Welcome back to the Quiet Between the Stars channel. I hope you have found a comfortable place to rest. Tonight, we are confronting something that bends the mind. Time and space are not separate things. They are woven together into a single fabric, and that fabric can stretch, warp, and curve depending on how much mass is nearby. Near a black hole, time slows to a crawl. In the emptiest voids between galaxy clusters, it flows almost undisturbed. The clock on your wall and the clock on a satellite orbiting Earth tick at measurably different rates, a difference of about 45 microseconds per day, enough that your phone's GPS must constantly correct for it. We will begin here, on Earth, where time moves at the pace you know. Then we will drift outward, past the moon, past the sun, into regions where gravity loosens its grip and time begins to behave differently. We will visit a neutron star, where a teaspoon of matter weighs 6 billion tons and time runs noticeably slower. We will approach the event horizon of a black hole, where time nearly stops for an outside observer. And finally, we will float into the great cosmic voids, the emptiest places in existence, where time flows as freely as it ever can. If these quiet explorations help you rest, or if you find comfort in understanding the universe a little better, please consider liking and subscribing. It helps others find this channel. Now, settle in. Let your breathing slow. The journey from the familiar tick of earthly clocks to the strange silence of deep space begins now. In the quietest depths of existence, far beneath the reach of any microscope or instrument humanity has ever devised, there lies a boundary. Not a wall, not a barrier, but a threshold where the very concepts of distance and duration begin to lose their meaning. This is the Planck scale, named after the German physicist Max Planck, who in 1899 derived a set of fundamental units from the constants of nature itself. The Planck length measures approximately 1.616 times 10 to the negative 35th meters. To grasp how impossibly small this is, consider that a single proton, the nucleus of a hydrogen atom, spans about 10 to the negative 15th meters. The Planck length is smaller than a proton by the same factor that a proton is smaller than a medium-sized city. If you were to enlarge a single atom to the size of the observable universe, the Planck length would still be smaller than a grain of sand within that expanded atom. This scale emerges not from arbitrary choice, but from the intersection of three fundamental constants. The speed of light, denoted c, travels at precisely 299,792,458 meters per second through the vacuum of space. The gravitational constant g, which governs the attraction between masses, equals 6.674 times 10 to the negative 11th cubic meters per kilogram per second squared. And the reduced Planck constant h bar, which sets the scale of quantum mechanical effects, measures 1.055 times 10 to the negative 34th joule seconds. When these three values are combined through dimensional analysis, they yield natural units of length, time, and mass that belong to no particular experiment or observation, but to the structure of physics itself. The Planck time follows from dividing the Planck length by the speed of light. It equals approximately 5.391 times 10 to the negative 44th seconds. In 1 second of ordinary experience, more Planck times elapse than there have been seconds since the Big Bang. The age of the universe, measured at 13.8 billion years, contains roughly 8 times 10 to the power of 60 Planck time intervals. Yet even this staggering number barely hints at the gulf between human perception and the quantum foundations of reality. At scales larger than the Planck length, spacetime behaves as a smooth, continuous fabric. Einstein's general relativity describes it as a 4-dimensional manifold that can stretch, curve, and ripple in response to mass and energy. Quantum mechanics, meanwhile, governs the behavior of particles and fields with extraordinary precision. The electron's magnetic moment has been measured to agree with theoretical predictions to better than 1 part in a trillion, making quantum electrodynamics the most accurately tested theory in all of science. But as distances shrink toward the Planck scale, these two frameworks begin to conflict. General relativity assumes spacetime is smooth at every scale, infinitely divisible, capable of being measured with arbitrary precision. Quantum mechanics, however, insists that measurement itself has limits. The Heisenberg uncertainty principle states that the product of the uncertainty in position and the uncertainty in momentum must always exceed h bar divided by 2. This is not a limitation of instruments, but a fundamental feature of nature. When attempting to probe distances smaller than the Planck length, a curious paradox emerges. To measure such tiny intervals would require photons or other particles with wavelengths shorter than 10 to the minus 35 meters. According to the relationship between wavelength and energy, such photons would carry energies exceeding the Planck energy of approximately 1.22 times 10 to the 19th gigaelectron volts. For comparison, the Large Hadron Collider, the most powerful particle accelerator ever built, achieves collision energies of about 13,000 gigaelectron volts, roughly a quadrillion times too weak. But energy concentrated in such a small region creates its own problem. According to general relativity, sufficient energy density curves spacetime. At the Planck scale, the energy required for measurement would curve spacetime so severely that it would form a black hole with a Schwarzschild radius comparable to the distance being measured. The act of observation would destroy the very thing being observed. Space and time, at this scale, become not merely difficult to measure, but potentially meaningless as separate concepts. The Planck mass, approximately 2.176 times 10 to the negative 8th kilograms, or about 22 micrograms, might seem surprisingly large compared to the tiny length and time scales. A grain of sand weighs roughly this amount. Yet this mass represents the threshold at which quantum gravitational effects become significant. A black hole with the Planck mass would have an event horizon equal to the Planck length and would evaporate through Hawking radiation in approximately 1 Planck time. Max Planck himself recognized the significance of these natural units. In his original 1899 paper, he wrote that they would retain their meaning for all times and all civilizations, even extraterrestrial and non-human ones. They depend on no particular choice of measurement system, no arbitrary definition of meters or seconds. They emerge from the universe's own constants, as fundamental as the laws of physics themselves. The temperature associated with the Planck scale reaches approximately 1.417 times 10 to the power of 32 Kelvin. At this temperature, thermal radiation would have wavelengths comparable to the Planck length. The early universe, in the first 10 to the minus 43 seconds after the Big Bang, existed at or near this temperature. During this epoch, known as the Planck era, all four fundamental forces may have been unified, and the distinction between space and time may not yet have crystallized into its current form. No experiment has directly probed the Planck scale, and none is likely to in the foreseeable future. The energy required exceeds anything achievable with current or imagined technology by factors of 10 trillion or more. Yet theoretical physicists have developed frameworks that attempt to describe what might occur at these scales. String theory proposes that fundamental particles are not points, but tiny vibrating strings with lengths near the Planck scale. Loop quantum gravity suggests that spacetime itself is quantized, woven from discrete loops of gravitational field with areas measured in Planck units. In loop quantum gravity, space is not infinitely divisible. The smallest possible area equals approximately 10 to the negative 70 square meters, and the smallest possible volume measures roughly 10 to the negative 105 cubic meters. Below these values, the concepts of area and volume simply do not apply. Space becomes granular, like a fabric that appears smooth from a distance, but reveals its weave under sufficient magnification. The implications ripple outward from these foundations. If spacetime is discrete at the Planck scale, then the number of possible configurations within any finite region becomes finite as well. A black hole's entropy, measured by the Bekenstein-Hawking formula, equals 1/4 of its event horizon area divided by the Planck area. A solar mass black hole with an event horizon radius of about 3 kilometers would have an entropy of approximately 10 to the 77th power in natural units, corresponding to roughly 10 to the 77th power possible internal configurations. The Planck scale represents not merely smallness, but a boundary of knowledge. Beyond it, the familiar concepts of distance, duration, and causality may require revision or replacement. The smooth spacetime of Einstein's equations may give way to something stranger, a quantum foam of fluctuating geometry, a network of discrete connections, or structures not yet imagined. For now, the Planck scale remains a theoretical horizon, a place where equations falter and intuition fails. Yet its existence shapes our understanding of everything built upon it. Every meter of distance, every second of time, every interaction between particles rests ultimately on foundations that reach down to these impossible depths, where the architecture of reality reveals its finest grain. At these impossible depths, where the Planck length marks the finest grain of spatial measurement, spacetime itself begins to lose its familiar character. The smooth, continuous fabric described by Einstein's field equations starts to tremble. What appears perfectly flat and featureless at ordinary scales reveals, under sufficient magnification, a seething, turbulent landscape. Physicists call this quantum foam, a term coined by John Wheeler in 1955 to describe the chaotic fluctuations that theory predicts must occur at the smallest measurable distances. The origin of this foam lies in one of the most fundamental principles of quantum mechanics, the Heisenberg uncertainty principle. Werner Heisenberg formulated this relationship in 1927, demonstrating that certain pairs of physical properties cannot both be known with arbitrary precision. The more accurately one measures a particle's position, the less accurately one can know its momentum, and vice versa. The product of these uncertainties can never fall below a specific value, approximately 5.27 times 10 to the negative 35th joule seconds divided by 2p. This uncertainty extends beyond particles to the fabric of spacetime itself. At scales approaching 1.6 times 10 to the negative 35th meters, the energy required to probe such tiny distances becomes so enormous that it warps the very space being measured. The uncertainty principle, combined with general relativity, creates a paradox. To measure distances smaller than the Planck length would require concentrating so much energy in so small a region that a black hole would form, hiding the measurement behind an event horizon. The act of observation destroys the possibility of observation. The quantum foam emerges from this fundamental tension. According to quantum field theory, empty space is never truly empty. Virtual particles constantly flicker in and out of existence, borrowing energy from the vacuum for brief moments permitted by the uncertainty principle. A virtual electron-positron pair might exist for approximately 10 to the minus 21 seconds before annihilating, their fleeting presence leaving no permanent trace, but contributing to measurable effects like the Lamb shift in hydrogen atoms, a tiny displacement of energy levels first detected in 1947 with a precision of about 4 parts per million. At the Planck scale, these quantum fluctuations affect not just particles, but geometry itself. The energy density of virtual particles becomes so extreme that spacetime curves and writhes. Tiny wormholes might form and collapse. Miniature black holes could appear and evaporate through Hawking radiation in times of approximately 10 to the minus 43 seconds. The smooth, four-dimensional manifold of general relativity dissolves into something resembling a froth, with topology changing from moment to moment. Imagine a perfectly calm ocean viewed from an airplane at cruising altitude. The surface appears smooth, almost glassy. Descend to 100 meters, and waves become visible. Drop to the surface itself, and the water reveals constant motion, ripples and splashes and turbulence at every scale. Continue shrinking, past the molecular level, past the atomic, down to distances 20 orders of magnitude smaller than a proton, and the very concept of a surface loses meaning. This is the nature of quantum foam. What seems solid and continuous at human scales becomes uncertain and fluctuating at the Planck scale. The mathematics describing this foam remains incomplete. General relativity treats spacetime as a smooth, differentiable manifold, a mathematical structure where calculus applies and distances can be measured with arbitrary precision. Quantum mechanics demands discreteness, probability, and fundamental limits on knowledge. These two frameworks, each spectacularly successful in its domain, resist unification. General relativity predicts the behavior of galaxies and the expansion of the universe with extraordinary accuracy. Quantum mechanics describes atomic transitions and particle interactions to precisions of 1 part in 10 billion. Yet combining them at the Planck scale produces infinities and contradictions. Several theoretical approaches attempt to describe quantum foam more rigorously. Loop quantum gravity, developed primarily by Abhay Ashtekar, Lee Smolin, and Carlo Rovelli beginning in the 1980s, proposes that space itself is quantized. In this framework, area and volume come in discrete units. The smallest possible area is approximately 10 to the negative 70 square meters, and the smallest volume is roughly 10 to the negative 105 cubic meters. Space resembles a fabric woven from tiny loops of gravitational field, with the foam arising naturally from quantum superpositions of different geometric configurations. String theory takes a different approach, suggesting that the fundamental constituents of reality are not point particles, but one-dimensional strings vibrating at specific frequencies. These strings have a characteristic length of approximately 10 to the minus 35 meters, close to the Planck length. In string theory, the foam-like structure of spacetime emerges from the quantum behavior of strings and the higher dimensional spaces they inhabit. The theory requires either 10 or 11 dimensions, with the extra dimensions curled up so tightly that they remain undetectable at current energies. Causal set theory proposes an even more radical picture. Spacetime is not continuous at all, but consists of discrete points connected by causal relationships. The foam is not a modification of smooth geometry, but a replacement for it. At the deepest level, there is no space and no time, only a network of events linked by the possibility of influence passing from one to another. The familiar space-time of experience emerges only at larger scales, like the apparent smoothness of a digital photograph that dissolves into individual pixels under magnification. Despite these theoretical frameworks, direct experimental evidence for quantum foam remains elusive. The energies required to probe the Planck scale exceed anything achievable with current or foreseeable technology. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of approximately 13 tera-electron-volts. Probing the Planck scale would require energies roughly a quadrillion times greater, about 10 to the 19th giga-electron-volts. No conceivable accelerator could achieve such energies. The required machine would need to be larger than the solar system. Yet indirect evidence might be accessible. Some theories predict that quantum foam could affect the propagation of light over cosmological distances. Photons traveling billions of light-years might accumulate tiny delays or energy shifts from their passage through fluctuating space-time. The Fermi Gamma-Ray Space Telescope has searched for such effects in gamma-ray bursts, explosions visible from distances exceeding 10 billion light-years. So far, observations show that photons of vastly different energies arrive simultaneously to within 1 part in 10 to the 17th power, placing stringent limits on certain models of quantum foam. Other experiments search for violations of Lorentz invariance, the principle that the laws of physics appear the same regardless of an observer's velocity or orientation. Some quantum gravity theories predict that space-time foam might introduce a preferred frame of reference, detectable through subtle asymmetries in particle physics experiments. Measurements of cosmic ray interactions and precision tests of atomic clocks have found no such violations, constraining the scale at which foam effects could appear. The quantum foam represents a frontier where physics confronts its own limitations. The smooth space-time that carries light across the cosmos, that bends around stars and stretches between galaxies, may be an approximation valid only at scales far larger than its own fundamental structure. Like the apparent solidity of matter, which dissolves into mostly empty space at atomic scales, the continuity of spacetime may be an emergent property, arising from something more fundamental that current theories can only glimpse. At this threshold, the architecture of reality reveals its deepest uncertainties. The foam churns at scales forever beyond direct observation, yet its existence shapes the consistency of physical law. Every measurement, every interaction, every moment of time rests on this seething foundation, where geometry itself becomes probabilistic, and the distinction between something and nothing blurs into quantum superposition. From this seething foundation, where geometry fluctuates and certainty dissolves, one constant emerges with absolute clarity. A number so fundamental that it appears in equations governing electromagnetism, quantum mechanics, and the structure of spacetime itself. This number is 299,792,458 meters per second, the speed at which light travels through the vacuum of space, and it represents far more than merely how fast photons move. It is the universal speed limit, the cosmic constant that binds together the very fabric of reality. The discovery of this limit came gradually, through centuries of careful measurement and theoretical insight. In 1676, the Danish astronomer Ole Rømer noticed something peculiar while observing the moons of Jupiter. The moon Io, which orbits Jupiter every 42.5 hours, appeared to eclipse at slightly different times, depending on Earth's position in its own orbit. When Earth was closest to Jupiter, the eclipses came about 11 minutes earlier than predicted. When Earth was farthest away, they arrived 11 minutes late. Rømer realized that light itself must take time to cross the varying distance between the planets, and from this discrepancy, he calculated light's speed at roughly 220,000 kilometers per second. Though his measurement was about 26% lower than the true value, Rømer had demonstrated something revolutionary. Light was not instantaneous. It traveled at a finite, measurable velocity. Over the following centuries, increasingly precise experiments refined this measurement. In 1849, Hippolyte Fizeau used a rotating toothed wheel to measure light speed on Earth, obtaining a value of 315,000 kilometers per second. Just a year later, Léon Foucault improved the technique using rotating mirrors, arriving at 298,000 kilometers per second, remarkably close to the modern value. By 1983, the measurement had become so precise that scientists redefined the meter itself in terms of light speed, declaring that 1 meter equals the distance light travels in exactly 1 divided by 299,792,458 of a second. The speed of light had become not just a measured quantity, but a defined constant, a cornerstone of the international system of units. Yet the true significance of this speed emerged not from measurement but from theory. In the 1860s, James Clerk Maxwell unified electricity and magnetism into a single mathematical framework, producing 4 elegant equations that described electromagnetic phenomena. When Maxwell solved these equations for waves propagating through empty space, He found that they traveled at a specific velocity determined entirely by two fundamental constants: the permittivity and permeability of free space. The calculated speed was 299,792 kilometers per second, matching the measured speed of light with extraordinary precision. Maxwell had discovered that light itself was an electromagnetic wave, and that its speed was woven into the basic structure of electromagnetism. This realization raised a profound question. If light traveled at a specific speed, what was it moving relative to? Sound waves travel through air at about 343 meters per second, but this speed is measured relative to the air itself. A person moving through the air would measure a different speed for sound depending on their motion. Physicists assumed that light must similarly travel through some medium, which they called the luminiferous ether, an invisible substance permeating all of space. The speed of light would then be measured relative to this ether, and Earth's motion through it should produce detectable variations in light's apparent speed. In 1887, Albert Michelson and Edward Morley designed an exquisitely sensitive experiment to detect Earth's motion through this hypothetical ether. Their interferometer split a beam of light into two perpendicular paths, reflected them back, and recombined them. If Earth were moving through the ether, light traveling along the direction of motion should experience a different round-trip time than light traveling perpendicular to it, producing an interference pattern that would shift as the apparatus rotated. The expected effect was small, corresponding to a path difference of about 0.4 wavelengths of light. But the interferometer was sensitive enough to detect shifts as small as 0.01 wavelengths. The result was null. No matter how the apparatus was oriented, no matter what time of year the experiment was performed, no shift appeared. Light traveled at the same speed in all directions, regardless of Earth's motion through space at 30 kilometers per second around the Sun. The ether, if it existed, was completely undetectable. This negative result became one of the most important experiments in the history of physics, a puzzle that would require a complete reimagining of space and time to resolve. The resolution came in 1905, when a 26-year-old patent clerk named Albert Einstein published a paper titled "On the Electrodynamics of Moving Bodies." Einstein began with two postulates. First, the laws of physics are the same in all inertial reference frames, meaning that no experiment can detect absolute motion through space. Second, the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. This second postulate seemed to contradict common sense. If a train moves at 100 kilometers per hour, and someone on the train throws a ball forward at 20 kilometers per hour, an observer on the ground sees the ball moving at 120 kilometers per hour. Velocities add. Yet Einstein declared that light does not follow this rule. A flashlight beam emitted from a spaceship traveling at 200,000 kilometers per second still travels at exactly 299,792 kilometers per second relative to a stationary observer, not at 499,792 kilometers per second as ordinary addition would suggest. The consequences of this postulate are extraordinary. For light to travel at the same speed for all observers, something else must give. That something is time and space themselves. Einstein showed that time passes at different rates for observers in relative motion, a phenomenon called time dilation. A clock moving at 90% of light speed ticks at only 44% of the rate of a stationary clock. At 99% of light speed, the moving clock ticks at just 14% of the stationary rate. At 99.99%, the ratio drops to 1.4%. As velocity approaches the speed of light, time dilation approaches infinity, meaning that time for the moving object would effectively stop relative to a stationary observer. This is not a theoretical abstraction. In 1971, Joseph Hafele and Richard Keating placed cesium atomic clocks on commercial aircraft and flew them around the world, comparing them to identical clocks that remained on the ground. The flying clocks lost about 59 nanoseconds due to their velocity relative to Earth's surface, while gaining about 273 nanoseconds due to gravitational effects at higher altitude, for a net gain of roughly 214 nanoseconds. These tiny differences, billionths of a second, matched Einstein's predictions with remarkable precision. Time dilation is real, measurable, and must be accounted for in technologies like the Global Positioning System, where satellite clocks gain 38 microseconds per day relative to ground clocks and must be continuously corrected to maintain accuracy. The speed of light also imposes a fundamental limit on causality. Nothing carrying information or energy can exceed this speed, because doing so would violate the logical structure of cause and effect. If a signal could travel faster than light, there would exist reference frames in which the signal arrived before it was sent, creating paradoxes where effects precede their causes. The speed of light is not merely a speed limit for objects. It is the speed at which causality itself propagates through the universe. Events separated by distances that light cannot cross in the available time are causally disconnected, unable to influence each other regardless of what forces or signals might be involved. This limit shapes the very structure of space-time. Every event in the universe possesses a light cone, a geometric boundary separating the regions it can influence from those it cannot. The future light cone contains all events that could possibly be affected by a signal traveling at or below light speed. The past light cone contains all events that could have influenced the present moment. Everything outside these cones is causally inaccessible, separated by what physicists call a space-like interval. The speed of light thus divides the universe into regions of possible connection and regions of permanent isolation, a structure that remains invariant for all observers regardless of their motion. At the quantum level, particles routinely approach this cosmic speed limit. In particle accelerators like the Large Hadron Collider at CERN, protons are accelerated to 99.9999991% of the speed of light, circling the 27-kilometer ring 11,245 times per second. At these velocities, the proton's relativistic mass increases by a factor of about 7,500, requiring enormous energies to achieve even tiny additional increases in speed. The closer they approach light speed, the more energy is required for each incremental gain, with the energy needed to reach exactly light speed being infinite. This asymptotic barrier ensures that massive particles can approach, but never reach the universal limit. Photons themselves, being massless, travel at exactly this speed from the moment of their creation. They experience no passage of time in their own reference frame. A photon emitted from a distant galaxy 10 billion years ago arrives at Earth having experienced, from its own perspective, no duration whatsoever. The journey that spans cosmic ages for observers embedded in space-time is instantaneous for the photon itself. This strange property arises directly from the mathematics of special relativity, where time dilation becomes infinite at light speed, compressing all external time into a single moment. The constancy of light speed thus reveals itself not as an arbitrary fact about electromagnetic radiation, but as a fundamental feature of reality's architecture. It connects the behavior of electric and magnetic fields to the structure of space-time, links the flow of time to the motion of observers, and establishes the causal boundaries that determine which events can influence which others. In this single number, 299,792,458 meters per second, the universe encodes its deepest rules about connection, separation, and the nature of existence itself. From this foundation of cosmic speed limits emerges one of the most counterintuitive discoveries in the history of physics. When Albert Einstein published his special theory of relativity in 1905, he revealed that time itself is not the universal constant humanity had always assumed. Instead, time flows differently depending on how fast an observer moves through space. This phenomenon, known as time dilation, transforms our understanding of reality from a universe with a single, shared clock to one where every moving object carries its own personal timepiece, each ticking at its own unique rate. The mathematics behind this effect emerges directly from the constancy of light's speed. Consider a simple thought experiment that Einstein himself contemplated. Imagine a clock that measures time by bouncing a pulse of light between two mirrors, one above the other. Each time the light completes a round trip, the clock registers one tick. For an observer standing beside this clock, the light travels straight up and straight down, covering a distance of perhaps 1 meter in each direction. At 299,792,458 meters per second, the timing is precise and predictable. Now imagine this same clock aboard a spacecraft traveling at half the speed of light, approximately 150,000 kilometers per second. From the perspective of someone watching from outside the ship, something remarkable occurs. The light pulse still travels at exactly 299,792,458 meters per second, as it must according to the fundamental constancy of light. But the mirrors are now moving sideways as the light travels between them. The pulse must therefore follow a diagonal path, traveling a greater distance to complete each round trip. Since the speed of light cannot change, the only variable that can adjust is time itself. The moving clock must tick more slowly. The precise relationship between velocity and time dilation follows a mathematical formula involving the Lorentz factor, named after Dutch physicist Hendrik Lorentz. This factor equals 1 divided by the square root of 1 minus the square of the velocity divided by the square of light's speed. At everyday speeds, this factor is so close to 1 that the difference is unmeasurable. A car traveling at 100 kilometers per hour experiences time dilation of approximately 0.000000000000001%. A difference so minuscule that it would take the age of the universe to accumulate even a single second of discrepancy. But as velocities approach a significant fraction of light speed, the effects become dramatic. At 10% of light speed, roughly 30,000 kilometers per second, time slows by about 0.5%. At 50% of light speed, time runs at 87% of its stationary rate. At 90% of light speed, time slows to 44%. At 99% of light speed, time crawls at just 14% of its normal pace. And at 99.9% of light speed, time dilates so severely that only 4.5% of normal time passes for the moving observer compared to someone at rest. This is not an illusion or a measurement artifact. Time genuinely passes more slowly for objects in motion. The effect has been confirmed through numerous experiments with extraordinary precision. In 1971, physicists Joseph Haffel and Richard Keating placed cesium atomic clocks aboard commercial aircraft and flew them around the world, comparing them to identical clocks that remained on the ground. The flying clocks lost approximately 59 nanoseconds during their eastward journey and gained about 273 nanoseconds traveling westward, matching the predictions of relativity when accounting for both the aircraft's velocity and the gravitational effects of altitude. More dramatic confirmation comes from particle physics. Muons, subatomic particles created when cosmic rays strike Earth's upper atmosphere, have a half-life of just 2.2 microseconds when measured at rest. Traveling at 99.94% of light speed, these particles should decay long before reaching Earth's surface, covering only about 660 meters in their brief existence. Yet detectors at sea level observe abundant muons arriving from the upper atmosphere, having traveled through 15 kilometers or more of air. From the muon's perspective, its internal clock runs normally, and it lives for just 2.2 microseconds. But from Earth's perspective, time dilation stretches the muon's lifespan by a factor of roughly 29, allowing it to survive the journey to the surface. The global positioning system provides perhaps the most practical demonstration of relativistic time dilation. GPS satellites orbit Earth at approximately 14,000 kilometers per hour, fast enough that their onboard atomic clocks lose about 7 microseconds per day due to their velocity relative to ground-based receivers. This effect alone would cause positioning errors of roughly 2 kilometers daily if left uncorrected. The satellite's clocks must be deliberately adjusted to compensate for this relativistic drift, a constant reminder that Einstein's century-old theory governs the technology in billions of pockets worldwide. The symmetry of time dilation presents one of relativity's most mind-bending aspects. If a spacecraft passes Earth at 80% of light speed, observers on Earth will measure the ship's clocks as running at 60% of normal speed, but observers aboard the spacecraft, looking back at Earth, will measure Earth's clocks as running at 60% of normal speed. Both observations are correct, Neither perspective is privileged. The apparent paradox resolves through careful consideration of simultaneity, another concept that Einstein showed to be relative rather than absolute. Events that appear simultaneous to one observer may occur at different times for another observer in motion. This leads to the famous twin paradox, a thought experiment that has puzzled students for over a century. Imagine two twins, one who remains on Earth while the other travels to a distant star at 90% of light speed and returns. For the traveling twin, the journey might take 10 years of personal time. But upon returning, the traveler finds that 23 years have passed on Earth. The stay-at-home twin has aged more than twice as much. This asymmetry arises because the traveling twin must accelerate and decelerate, changing reference frames in ways that break the symmetry between the two perspectives. The twin who feels the acceleration is the one who ages less. At the extremes of velocity, time dilation approaches infinity. A particle traveling at 99.9999% of light speed experiences time at roughly 0.14% of the rate experienced by stationary observers. For every second that passes for the particle, nearly 12 minutes pass for the rest of the universe. At 99.999999% of light speed, the ratio becomes even more extreme, with thousands of years passing externally for every subjective second. Particles at the Large Hadron Collider routinely achieve such velocities, their internal clocks nearly frozen relative to the laboratory equipment that tracks their collisions. The energy required to achieve such speeds increases without bound as velocity approaches light speed. This is because relativistic mass, the effective resistance to acceleration, grows according to the same Lorentz factor that governs time dilation. At 99% of light speed, a particle behaves as if it has 7 times its rest mass. At 99.9%, the factor rises to 22. Accelerating any object with mass to exactly light speed would require infinite energy, which is why the speed of light represents an absolute barrier for material objects. Time dilation thus reveals itself as a fundamental feature of motion through space-time. Every journey through space is simultaneously a journey through time, with the rate of temporal passage depending on the speed of spatial travel. The faster an object moves through space, the slower it moves through time, as if the total rate of motion through the 4 dimensions of space-time must remain constant. This deep connection between space and time, first glimpsed through the constancy of light speed, transforms them from separate entities into a unified fabric, where motion in one dimension inevitably affects motion in the others. This unity of space and time reveals itself not only in the slowing of clocks, but in the contraction of rulers. Just as motion through space affects the passage of time, it equally affects the measurement of distance itself. An object moving at high velocity relative to an observer appears compressed along its direction of travel, shortened in a way that becomes more pronounced as speed increases toward the cosmic limit. This phenomenon, known as length contraction, stands as the spatial counterpart to time dilation, 2 faces of the same relativistic geometry. The mathematics describing this contraction follows a pattern identical to time dilation, governed by the same Lorentz factor that Einstein derived from the constancy of light speed. An object moving at 90% of light speed appears compressed to roughly 44% of its rest length when measured by a stationary observer. At 99% of light speed, this compression becomes extreme, with the object appearing only 14% as long as it would at rest. At 99.9%, the measured length shrinks to just 4.5% of the original. The formula connecting these values involves the square root of 1 minus the velocity squared divided by the speed of light squared, the same mathematical relationship that governs temporal distortion. Consider a spacecraft 100 meters long at rest in its hangar. As this vessel accelerates to half the speed of light, approximately 149,896 kilometers per second, an observer on Earth would measure its length as roughly 86.6 meters. The spacecraft itself experiences no internal change. Its passengers feel no compression, its instruments detect no shrinking, its structural integrity remains unaffected. Yet from the perspective of anyone watching from outside, the ship has genuinely contracted along its direction of motion. This is not an optical illusion or a trick of measurement. The contraction represents a real geometric transformation of space itself, as experienced from different reference frames. The reciprocal nature of this effect mirrors the symmetry found in time dilation. Just as each observer sees the other's clock running slow, each observer sees the other's rulers contracted. The spacecraft's crew, looking back at Earth, would measure our planet as compressed along the direction of their motion. Earth, normally 12,742 kilometers in diameter, would appear flattened into an ellipsoid, shortened along the axis of the ship's velocity, while maintaining its full width perpendicular to that motion. Both measurements are correct within their respective frames of reference. Neither observer occupies a privileged position from which to declare the true length of any object. This apparent paradox dissolves when we recognize that length, like time, is not an absolute property of objects, but a relationship between objects and observers. The concept of a single, universal length that all observers must agree upon belongs to the intuitive physics of everyday experience, where velocities remain negligible compared to light. In that familiar realm, a meter stick measures 1 meter for everyone, regardless of their state of motion. But this agreement emerges only because the relativistic effects at ordinary speeds are too small to detect. A car traveling at 100 kilometers per hour contracts by roughly 1 part in 10 to the 14th power, a change of about 100 femtometers, smaller than the diameter of a single atomic nucleus. The physical reality of length contraction was dramatically confirmed through observations of cosmic ray muons, the same particles whose extended lifetimes demonstrated time dilation. These muons are created when high-energy protons from deep space collide with nitrogen and oxygen molecules in Earth's upper atmosphere, typically at altitudes around 15 kilometers. With a half-life of only 2.2 microseconds and velocities near 99.9% of light speed, classical physics predicts they should travel only about 660 meters before half of them decay. Yet detectors at sea level register far more muons than this calculation allows. From the muon's perspective, the explanation involves length contraction rather than time dilation. The muon experiences its proper half-life of 2.2 microseconds without any relativistic extension. However, the distance to Earth's surface appears dramatically shortened due to the muon's high velocity relative to the atmosphere. That 15-kilometer journey contracts to roughly 670 meters in the muon's reference frame, a distance easily traversed within its brief existence. Both explanations, time dilation from Earth's perspective and length contraction from the muon's perspective, yield identical predictions for how many muons reach the surface. This consistency confirms that these phenomena are not separate effects, but complementary aspects of space-time geometry. The geometry underlying length contraction becomes clearer when visualized in the four-dimensional framework that Hermann Minkowski introduced in 1908. In this representation, space and time merge into a single continuum, where every object traces a path called a world line. A stationary object moves only through time, its world line extending vertically on a space-time diagram. A moving object's world line tilts, angling through both space and time simultaneously. The faster the object moves, the more its world line tilts toward the horizontal, approaching but never reaching the 45-degree angle that represents light's trajectory. When observers in relative motion attempt to measure the length of an object, they are effectively taking different slices through this four-dimensional structure. Each observer's definition of simultaneous, the set of events they consider to be happening at the same moment, differs from other observers moving at different velocities. Measuring length requires determining the positions of an object's front and back at the same instant. But if observers disagree about which events are simultaneous, they will necessarily disagree about the spatial separation between those events. Length contraction emerges from this relativity of simultaneity, a geometric consequence of how different reference frames slice through space-time at different angles. This connection to simultaneity explains why contraction occurs only along the direction of motion. Perpendicular to the velocity, observers agree about simultaneity and therefore agree about distances. A spacecraft 100 meters long and 20 meters wide, traveling at 90% of light speed, appears 44 meters long but still 20 meters wide to a stationary observer. The compression affects only the dimension aligned with the relative velocity, creating the flattening effect that would make spheres appear as oblate ellipsoids and cubes appear as rectangular prisms. The practical implications of length contraction extend into the design of particle accelerators, where protons and electrons routinely approach light speed. In the Large Hadron Collider at CERN, protons circulate at 99.999991% of the speed of light, corresponding to a Lorentz factor of approximately 7,460. From the perspective of these protons, the 27-kilometer circumference of the accelerator contracts to roughly 3.6 meters. The entire ring, spanning the border between Switzerland and France, compresses into a distance shorter than a typical living room. This extreme contraction affects how the protons interact with the accelerator's magnetic fields and must be accounted for in the precise timing of particle collisions. Length contraction also influences the electromagnetic interactions between charged particles. A wire carrying electric current contains electrons drifting slowly through a lattice of positive ions. In the wire's rest frame, the positive and negative charges balance perfectly, creating no net electric field outside the wire. But from the perspective of a charge moving parallel to the wire, the spacing between the positive ions contracts differently than the spacing between the moving electrons, creating an apparent charge imbalance. This imbalance produces an electric field that exerts force on the moving charge, a force we recognize as magnetism. The magnetic force between current-carrying wires thus emerges as a relativistic effect of length contraction, unifying electricity and magnetism as aspects of a single electromagnetic phenomenon viewed from different reference frames. This unification of electricity and magnetism hints at something deeper still, a mathematical structure that binds space and time into a single geometric entity. The year after Einstein published his special theory of relativity, his former mathematics professor Hermann Minkowski recognized that the equations describing time dilation and length contraction were not merely clever formulas, but reflections of a profound geometric truth. In 1908, Minkowski declared to an audience of scientists that henceforth space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. This union takes the form of a four-dimensional continuum, a mathematical space where every event is specified not by 3 coordinates, but by 4. A meeting between friends requires not just a location, the corner of 5th Avenue and 42nd Street, but also a time, 3 o'clock on Tuesday afternoon. Without all 4 pieces of information, the meeting cannot occur. This observation seems almost trivially obvious, yet its mathematical formalization reveals that space and time are not merely convenient labels, but components of a unified geometric structure with its own intrinsic properties. In ordinary 3-dimensional space, the distance between 2 points follows the Pythagorean theorem. If one point lies 3 meters east and 4 meters north of another, the straight line distance between them measures 5 meters, the square root of 9 plus 16. This relationship holds regardless of how we orient our coordinate system. We might choose to align our axes with the compass directions or rotate them by any angle. Yet the distance between the points remains invariant at 5 meters. Distance is a geometric property of space itself, not an artifact of our chosen coordinates. Minkowski discovered that space-time possesses an analogous invariant quantity, though with a crucial difference. The space-time interval between 2 events combines spatial separation and temporal separation, but with opposite signs. If 2 events occur 1 light-second apart in space and 2 seconds apart in time, the space-time interval is not the sum of these squared, but their difference. Using the speed of light as a conversion factor, the spatial separation of 1 light second equals roughly 299,792 kilometers, and the interval calculation yields a quantity that remains constant regardless of which inertial reference frame performs the measurement. This mathematical structure explains why time dilation and length contraction occur in precisely the amounts they do. When an observer moves relative to another, their coordinate axes rotate within 4-dimensional spacetime, mixing what one observer calls space with what the other calls time. A clock moving through space appears to tick slowly because part of its temporal motion has been redirected into spatial motion. The total space-time interval traversed by the clock remains unchanged, but its projection onto the time axis shrinks, while its projection onto the spatial axes grows. Consider two events: the departure of a spacecraft from Earth and its arrival at a star 4 light-years distant. An observer on Earth measures these events as separated by 4 light-years in space and 5 years in time. The space-time interval, calculated as the square root of 25 minus 16, equals 3 light-years. A passenger aboard the spacecraft, traveling at 80% of light speed, measures the same interval of 3 light-years, but the components differ. For the passenger, the spatial separation between departure and arrival is 0. Both events occur at the same location within the ship, so the entire interval appears as proper time. The passenger ages 3 years during the journey, while Earth observers age 5 years, yet both agree on the space-time interval connecting the two events. This geometry of spacetime possesses a peculiar character that distinguishes it from ordinary Euclidean space. In Euclidean geometry, the shortest path between 2 points is always a straight line, and this distance is always positive. In spacetime, the interval between events can be positive, negative, or 0, depending on whether the separation is primarily temporal, primarily spatial, or exactly balanced between the two. Events connected by light signals have 0 space-time interval, a property that defines the light cone structure of space-time. The light cone of any event divides all of space-time into distinct regions. Events within the future light cone can be influenced by the original event, as signals traveling at or below light speed can reach them. Events within the past light cone could have influenced the original event. Events outside both cones, in the elsewhere region, are causally disconnected, neither able to influence nor be influenced by the original event through any physical process. This causal structure is absolute, agreed upon by all observers regardless of their motion. While observers may disagree about the time order of events in the elsewhere region, they always agree about which events lie within each other's light cones. The geometry of spacetime also reveals why nothing can exceed the speed of light. As an object accelerates, its world line, the path it traces through 4-dimensional space-time, tilts increasingly toward the spatial axis. At light speed, the world line would become parallel to the light cone itself, requiring infinite energy to achieve. Beyond light speed, the world line would tilt outside the light cone entirely, entering the elsewhere region where cause and effect become scrambled. An object traveling faster than light in one reference frame would appear to travel backward in time in another frame, creating paradoxes where effects precede their causes. The mathematical machinery describing this geometry employs tensors, multidimensional arrays of numbers that transform in specific ways when coordinates change. The metric tensor of flat spacetime, known as the Minkowski metric, encodes the rule for calculating spacetime intervals. Its components form a simple diagonal matrix with values of -1 for the time component and +1 for each spatial component, or vice versa depending on convention. This tensor serves as the foundation upon which all of special relativity rests, a geometric object that captures the essential structure of spacetime in the absence of gravity. World lines through this four-dimensional landscape carry physical meaning. A particle at rest traces a vertical line through space-time, advancing through time without moving through space. A particle in uniform motion traces a tilted straight line, its angle determined by velocity. An accelerating particle traces a curved world line, bending through space-time as its velocity changes. The proper time experienced by any particle equals the space-time interval along its world line, measured in units where the speed of light equals 1. This geometric perspective transforms the laws of physics into statements about the shapes of world lines and the intervals between events. Conservation of energy and momentum becomes a statement about four vectors, mathematical objects with one temporal and three spatial components that maintain their magnitude under coordinate transformations. The energy and momentum of a particle combine into a single four-momentum vector, whose magnitude equals the particle's rest mass multiplied by the speed of light squared. This relationship, expressed as the famous equation relating energy, momentum, and mass, emerges naturally from the geometry of spacetime rather than appearing as an arbitrary postulate. The fabric of spacetime, woven from these mathematical threads, provides the stage upon which all physical phenomena unfold. Particles trace their world lines through this four-dimensional arena, interacting at events where world lines intersect. Fields permeate the continuum, their values defined at every point in space and moment in time. The electromagnetic field, the strong and weak nuclear forces, all exist as structures within spacetime, their dynamics governed by equations that respect the geometric symmetries Minkowski revealed. Yet this elegant fabric remains flat, its static backdrop unaffected by the matter and energy it contains. The space-time of special relativity curves only through the choice of coordinates, not through any intrinsic property of the geometry itself. A decade after Minkowski's insight, Einstein would discover that gravity arises precisely from the curvature of this fabric, that mass and energy warp the geometry of space-time itself, transforming the passive stage into an active participant in the cosmic drama. The transformation began with a thought experiment, a question Einstein posed to himself in 1907 while working at the patent office in Bern. He imagined a person falling freely from the roof of a building and realized that during the fall, the person would feel no gravitational force at all. Objects released from the person's pockets would float beside them, accelerating towards the ground at precisely the same rate. In that moment of free fall, gravity would seem to vanish entirely. This insight, which Einstein later called the happiest thought of his life, contained the seed of a revolution. If acceleration and gravity produce identical effects, then perhaps they share a deeper identity. A person standing in a closed elevator accelerating upward at 9.8 meters per second squared would feel exactly the same force pressing them against the floor as someone standing on Earth's surface. No experiment conducted inside the elevator could distinguish between the two situations. This principle of equivalence became the cornerstone upon which Einstein would construct his general theory of relativity over the following 8 years. The mathematics required to express this vision did not yet exist in Einstein's toolkit. He needed a geometry capable of describing curved spaces, surfaces that bend and warp in ways that Euclidean geometry could never capture. His friend Marcel Grossmann introduced him to the work of 19th-century mathematicians, particularly Bernhard Riemann, who had developed the mathematical framework for analyzing spaces of arbitrary curvature. In Riemannian geometry, the properties of space vary from point to point, described by a mathematical object called the metric tensor, a collection of numbers that specify how distances and angles behave at each location. Consider the surface of a sphere, a two-dimensional curved space embedded in 3 dimensions. On this surface, the rules of Euclidean geometry fail. Parallel lines, which never meet on a flat plane, converge and intersect on a sphere. The angles of a triangle sum to more than 180 degrees, with the excess proportional to the triangle's area. The shortest path between 2 points follows a great circle, curving across the surface rather than cutting through the interior. These properties arise not from any external force, but from the intrinsic geometry of the surface itself. Einstein recognized that gravity could be understood in precisely this way. Rather than a force pulling objects toward massive bodies, gravity emerges from the curvature of space-time itself. Mass and energy warp the 4-dimensional fabric, and objects moving through this curved geometry follow the straightest possible paths, called geodesics. What we perceive as gravitational attraction is simply the natural motion of objects through curved space-time. No force required. The mathematical expression of this insight took the form of the Einstein field equations, published in November 1915. These equations relate the curvature of space-time, encoded in the Einstein tensor, to the distribution of matter and energy, described by the stress-energy tensor. The relationship involves Newton's gravitational constant, approximately 6.674 times 10 to the negative 11th cubic meters per kilogram per second squared, and the speed of light raised to the 4th power. The equations are notoriously difficult to solve, comprising 10 coupled non-linear partial differential equations that must be satisfied simultaneously. Yet even before the full theory was complete, Einstein extracted a prediction that would confirm his revolutionary vision. Mercury, the innermost planet, traces an elliptical orbit around the Sun that slowly rotates over time, its perihelion advancing by about 574 arcseconds per century. Newtonian gravity, accounting for the gravitational tugs of other planets, predicted 531 arcseconds. The remaining 43 arcseconds per century had puzzled astronomers for decades, some even proposing an unseen planet called Vulcan to explain the discrepancy. Einstein's equations, applied to the curved space-time around the Sun, predicted exactly 43 arcseconds of additional precession. When the calculation yielded this precise match, Einstein reported that his heart palpitated with excitement. The curvature of space-time near a massive object can be visualized through the familiar analogy of a bowling ball resting on a stretched rubber sheet. The ball creates a depression, and smaller objects rolling nearby curve toward it, not because of any direct attraction, but because the surface itself guides their motion. This analogy captures the essence of general relativity. Though it necessarily simplifies the 4-dimensional reality, into two dimensions we can picture. The strength of space-time curvature depends on how much mass is concentrated in how small a region. Near Earth's surface, the curvature is gentle, producing the familiar acceleration of 9.8 meters per second squared. The Sun curves space-time more severely, bending the paths of planets into elliptical orbits with periods ranging from Mercury's 88 days to Neptune's 165 years. A white dwarf, packing roughly the Sun's mass into a sphere the size of Earth, creates curvature strong enough to produce measurable effects on light passing nearby. This bending of light provided the first dramatic confirmation of general relativity. During the total solar eclipse of May 29, 1919, British expeditions to Sobral, Brazil, and Principe Island off the coast of Africa photographed stars near the Sun's obscured disk. Einstein's theory predicted that starlight grazing the Sun would deflect by 1.75 arcseconds, twice the value that Newtonian physics would suggest. The measured deflections, approximately 1.61 arcseconds at Sobral and 1.98 arcseconds at Principe, confirmed Einstein's prediction within experimental uncertainty. Headlines around the world announced that Newton had been overthrown, and Einstein became an international celebrity overnight. The metric tensor that describes curved space-time contains all the information needed to calculate distances, times, and the paths of objects and light. For the spacetime around a spherically symmetric, non-rotating mass, Carl Schwarzschild found an exact solution to Einstein's equations in December 1915, mere weeks after their publication. The Schwarzschild metric reveals how time slows and space stretches as one approaches a massive body, effects that become extreme as the mass concentrates into smaller volumes. At the surface of the Sun, clocks run slower by about 2 parts per million, compared to clocks far from any gravitational influence. On the surface of a neutron star, where a mass comparable to the Sun compresses into a sphere roughly 20 kilometers across, time dilates by approximately 20 to 30%. The curvature there bends space so severely that a neutron star's surface area exceeds what Euclidean geometry would predict for its circumference, the extra space folded into the warped geometry. This interplay between mass and geometry operates in both directions. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. The equations couple geometry and matter in a dynamic feedback loop, each influencing the other in ways that make general relativity far more complex than Newtonian gravity. The theory is non-linear, meaning that gravitational fields themselves carry energy, which in turn generates additional gravity. Two gravitational waves passing through the same region interact with each other, a phenomenon with no analog in the linear equations of electromagnetism. The predictions of general relativity have been confirmed with extraordinary precision over the past century. The Gravity Probe B satellite, launched in 2004, measured the geodetic effect and frame dragging around Earth with accuracies reaching parts per million. The geodetic precession, caused by motion through curved spacetime, matched Einstein's prediction of 6.6 arcseconds per year to within 0.28%. Frame dragging, the twisting of spacetime by Earth's rotation, was confirmed at 37 milliarcseconds per year, agreeing with theory to within 19%. binary pulsars provide natural laboratories for testing general relativity under extreme conditions. The Hulse-Taylor pulsar, discovered in 1974, consists of two neutron stars orbiting each other with a period of 7.75 hours. Over decades of observation, the orbit has decayed at precisely the rate predicted by general relativity for a system radiating gravitational waves, losing energy at approximately 7.4 times 10 to the 24th watts. This indirect detection of gravitational radiation earned Hulse and Taylor the Nobel Prize in 1993. The fabric of spacetime, once thought to be a passive stage, reveals itself as a dynamic participant in the cosmic drama. It bends around stars, stretches near black holes, and ripples with the passage of gravitational waves. The geometry of the universe responds to every concentration of energy, from the gentle curvature around planets to the extreme warping near the densest objects known. In this curved arena, time itself flows at different rates, clocks ticking faster in the valleys between mountains of mass, slower in the depths of gravitational wells. This difference in the flow of time, this gravitational time dilation, manifests not as an abstract mathematical curiosity, but as a measurable physical reality that affects technology orbiting overhead at this very moment. The Global Positioning System, that network of 31 satellites circling Earth at an altitude of approximately 20,200 kilometers, depends entirely on accounting for the warping of time by gravity. Each satellite carries atomic clocks precise to within a few nanoseconds per day, and these clocks tick faster than identical clocks on Earth's surface by exactly 45.9 microseconds every 24 hours. This acceleration occurs because the satellites orbit in a region of weaker gravitational curvature, where space-time is less compressed, where time flows more freely toward the future. But velocity also affects time, and the satellites move at roughly 3.9 kilometers per second relative to observers on the ground. This motion produces a special relativistic time dilation that slows the satellite clocks by 7.2 microseconds per day. The two effects work in opposition, gravity speeding the clocks while motion slows them, and the net result is that satellite clocks gain 38.7 microseconds daily compared to their Earth-bound counterparts. Without correcting for this discrepancy, GPS positions would drift by approximately 10 kilometers per day, rendering the system useless for navigation. The engineers who designed GPS had to program relativistic corrections into the satellite software, building Einstein's equations directly into the firmware that guides aircraft to runways and ambulances to emergencies. The mathematics describing this temporal distortion emerges from the Schwarzschild metric, a solution to Einstein's field equations discovered by the German physicist Karl Schwarzschild in 1916, just months before his death from illness contracted on the Russian front of World War I. His solution describes the geometry of space-time around a spherically symmetric, non-rotating mass, and from it flows a precise formula for gravitational time dilation. A clock at distance r from a mass m ticks slower than a clock infinitely far away, by a factor equal to the square root of 1 minus the Schwarzschild radius divided by AR. For Earth, with a Schwarzschild radius of merely 8.87 millimeters, This factor differs from unity by only about 1 part in a billion at the surface. Yet this billionth of a difference accumulates, second by second, into measurable discrepancies. The Pound-Rebka experiment of 1961 confirmed this gravitational redshift with remarkable precision. Robert Pound and Glenn Rebka placed gamma-ray sources at the top and bottom of a 22.5-meter tower at Harvard University, using the Moosbauer effect to achieve extraordinary spectral resolution. Photons climbing upward against Earth's gravity lost energy, their frequency shifting toward the red by 2.5 parts in 10 to the 15th power, exactly as general relativity predicted. This shift occurs because time runs faster at the top of the tower than at the bottom, and frequency is simply the inverse of the time between wave crests. A photon emitted at the bottom, where time flows slowly, arrives at the top, where time flows faster, and observers there perceive fewer wave crests passing per second of their quicker time. Gravity probe A, launched in 1976, extended this measurement to far greater heights. A hydrogen maser clock, the most stable frequency standard then available, rode a Scout rocket to an altitude of 10,000 kilometers before falling back to Earth. During its 2-hour flight, the clock's frequency was compared continuously with an identical maser on the ground. The results confirmed gravitational time dilation to within 70 parts per million, a triumph of experimental physics that validated decades of theoretical prediction. The effect intensifies dramatically near objects more massive than Earth. On the surface of the Sun, where gravity is 28 times stronger than terrestrial gravity, time runs slower by about 2 parts per million compared to distant space. A clock on the solar surface would lose roughly 1 minute per year relative to a clock far from any gravitational influence. This seems modest until one considers denser objects. A white dwarf star, with a mass comparable to the Sun compressed into a sphere the size of Earth, produces gravitational time dilation of several parts per 10,000. On the surface of Sirius B, the nearest white dwarf at 8.6 light-years distant, clocks tick measurably slower than in the surrounding space. Neutron stars push this effect to extremes that challenge intuition. These stellar remnants, formed in the gravitational collapse of massive stars, pack roughly 1.4 solar masses into spheres merely 20 kilometers across. The surface gravity reaches 200 billion times Earth's gravity, and the escape velocity approaches 100,000 kilometers per second, a third the speed of light. At such a surface, time dilation becomes profound. Clocks there run approximately 20 to 30% slower than clocks in distant space, depending on the star's precise mass and radius. An observer watching a neutron star from afar would see events on its surface unfold in slow motion, stretched and languorous, while an observer on the surface would perceive distant events as accelerated, rushing past at a frantic pace. The pulsar in the Crab Nebula, spinning 30 times per second, provides a natural clock embedded in intense gravitational curvature. Its regular radio pulses, arriving at Earth with extraordinary precision, carry information about the space-time geometry near its surface. Astronomers have used pulsar timing to test general relativity with exquisite accuracy, finding agreement with Einstein's predictions to better than 1 part in 10,000. As mass concentrates further, time dilation approaches its ultimate limit. Near a black hole, where the Schwarzschild radius marks the boundary of the event horizon, the factor describing time dilation approaches zero. At exactly the event horizon, time as measured by distant observers stops entirely. A clock falling toward a black hole would appear to slow progressively, its ticks stretching longer and longer, the final tick before crossing the horizon extended to infinite duration from the perspective of anyone watching from outside. The clock itself, from its own perspective, would continue ticking normally, crossing the horizon in finite proper time, but its signals would never escape to tell the tale. This asymmetry between local and distant time lies at the heart of gravitational time dilation. Every observer measures time passing at 1 second per second in their own reference frame. The difference emerges only in comparison when clocks at different gravitational potentials are brought together or their signals compared across space. The GPS satellites do not experience their clocks as running fast. Astronauts aboard the International Station do not feel time passing slowly. These effects reveal themselves only through the patient accumulation of discrepancies, through the comparison of atomic transitions separated by altitude or gravitational potential. And nowhere does this comparison reveal more extreme discrepancies than in the vicinity of objects so dense that space-time itself bends beyond recognition. The mathematics that Einstein published in 1915 contained within it a prediction so strange that even he doubted its physical reality. When Karl Schwarzschild, a German physicist serving in the Russian front during World War I, solved Einstein's field equations for a spherically symmetric mass, he discovered a radius at which the equations behaved peculiarly. For any mass compressed within this critical radius, space-time would curve so severely that nothing, not light, not information, not causality itself, could escape outward. This critical distance, now called the Schwarzschild radius, depends only on mass. For the Sun, it measures approximately 2.95 kilometers. For the Earth, merely 8.9 millimeters. For a human body, about 10 to the minus 23 meters, far smaller than a proton. Under normal circumstances, matter cannot compress to such densities. But the universe, patient and vast, creates conditions where gravity overwhelms all other forces, crushing stellar cores into regions smaller than cities, yet containing masses greater than suns. When a star more massive than roughly 25 solar masses exhausts its nuclear fuel, the outward pressure that balanced gravity for millions of years vanishes within seconds. The core collapses at velocities approaching 70,000 kilometers per second, roughly a quarter the speed of light. Within milliseconds, matter that once occupied a volume larger than Earth compresses into a sphere perhaps 20 kilometers across. If the remaining mass exceeds approximately 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, no known force in physics can halt the collapse. Neutron degeneracy pressure fails. The matter continues falling inward, crossing its own Schwarzschild radius, vanishing from the observable universe behind a boundary of no return. This boundary, the event horizon, represents not a physical surface but a mathematical one. A sphere in space-time, where the escape velocity equals the speed of light. At this radius, the curvature of space-time becomes so extreme that all future directed paths point inward. Just as on Earth's surface all directions except straight up lead eventually to lower altitudes, at the event horizon all directions through spacetime lead toward the central singularity. The horizon itself feels like nothing to a falling observer. No wall, no membrane, no sudden transition marks the crossing. Yet this invisible boundary separates two fundamentally different regions of the universe. One where escape remains possible, and one where the future contains only the singularity. The time dilation near this boundary approaches infinity in a mathematically precise way. At a distance of 1.5 Schwarzschild radii from the center, time passes at roughly 58% the rate of distant observers. At 1.1 Schwarzschild radii, this drops to about 30%. At 1.01 Schwarzschild radii, merely 10%. The formula governing this relationship involves the square root of 1 minus the Schwarzschild radius divided by the observer's radius. As the observer approaches the horizon, this factor approaches zero, and time dilation approaches infinity. Consider Cygnus X1, a black hole approximately 7,200 light-years from Earth, first identified through its X-ray emissions in 1964. With a mass of roughly 21 solar masses, its Schwarzschild radius extends about 62 kilometers. A clock hovering at 100 kilometers from its center, just 38 kilometers above the event horizon, would tick at approximately 62% the rate of clocks on Earth. At 70 kilometers, this slows to roughly 33%. At 63 kilometers, barely 1 kilometer above the horizon, time would crawl at roughly 13% of its distant rate. Each second experienced by the hovering observer would correspond to nearly 8 seconds passing in the wider universe. But hovering requires thrust, and the thrust required increases without bound as one approaches the horizon. At the photon sphere, located at 1.5 Schwarzschild radii, light itself can orbit the black hole in unstable circular paths. Inside this radius, no stable orbits exist. Any object must either fall inward or expend ever-increasing energy to maintain its position. The acceleration required to hover at 1.01 Schwarzschild radii exceeds 10 to the 12th meters per second squared, roughly 100 billion times Earth's surface gravity. No material structure could withstand such forces. For a freely falling observer, the experience differs profoundly from the view of distant watchers. An astronaut falling feet first toward a stellar mass black hole would experience tidal forces, the difference in gravitational pull between their feet and head. For Cygnus X1, these tidal forces would become lethal well before reaching the horizon, stretching the body in a process physicists call spaghettification. The difference in gravitational acceleration across a 2-meter human body would exceed 10,000 Gs at roughly 400 kilometers from the center, tearing tissue apart at the molecular level. Supermassive black holes offer gentler passage. Sagittarius, a star, the 4 million solar mass black hole at the center of our galaxy, possesses a Schwarzschild radius of approximately 12 million kilometers, about 17 times the radius of the Sun. Because tidal forces scale inversely with the square of the black hole's mass for a given distance from the horizon, an observer falling into Sagittarius AI would experience tidal accelerations of only about 0.001 Gs per meter at the event horizon. They could cross this boundary intact, alive, unaware of the precise moment of no return. Yet from the perspective of distant observers, this crossing would never complete. Light emitted by the falling astronaut would redshift progressively as they approached the horizon. Photons carrying the image of their final moments would stretch to longer and longer wavelengths, their frequency dropping, their energy diminishing. A photon emitted at 1.01 Schwarzschild radii would arrive at distant telescopes with only 10% of its original frequency. At 1.001 radii, roughly 3%, the astronaut's image would dim and redden, frozen in an eternal approach that asymptotically slows but never quite reaches the horizon. This is not merely an optical illusion, but a fundamental feature of spacetime geometry. The coordinate time required for light to travel from near the horizon to distant observers genuinely approaches infinity. The last photon the astronaut emits before crossing would take infinite coordinate time to escape. In practice, this means the photon's wavelength would stretch beyond detection, redshifting through infrared, microwave, radio, until its energy dropped below any measurable threshold. The astronaut would fade from view, their final image persisting as an ever-dimmer ghost painted on the horizon's edge. Inside the horizon, the roles of space and time exchange in a mathematical sense. The radial coordinate, which outside the horizon represents distance, becomes time-like. The time coordinate becomes space-like. This means that moving toward the singularity is no longer a choice in space, but an inevitability in time. Just as observers outside the horizon cannot prevent themselves from moving forward in time, observers inside cannot prevent themselves from moving toward smaller radii. The singularity lies not at a place, but at a time, a future moment that all internal world lines must eventually reach. The journey from horizon to singularity takes finite proper time, measurable by the falling observer's own clock. For a Schwarzschild black hole, this duration equals roughly pi times the Schwarzschild radius divided by the speed of light. For Cygnus X1, approximately 0.0006 seconds. For Sagittarius, a star, roughly 64 seconds. For the supermassive black holes at the centers of giant elliptical galaxies, with masses exceeding 10 billion suns, this final journey could last hours. During this descent, the observer would witness the external universe accelerate. Light falling in behind them would blue shift, compressing the entire future history of the cosmos into their remaining moments. The mathematical details depend on the observer's trajectory and the black hole's properties, but the general principle holds. The universe outside ages rapidly as the observer's proper time ticks toward its end. At the singularity itself, current physics breaks down entirely. Density approaches infinity. Space-time curvature becomes undefined. The equations of general relativity produce nonsensical results, signaling not a physical infinity, but the failure of the theory to describe conditions so extreme. Most physicists believe that quantum gravitational effects, currently beyond our theoretical understanding, must modify the singularity's nature. Perhaps space-time dissolves into quantum foam at the Planck scale. Perhaps the singularity connects to other regions of space-time through structures we cannot yet describe. The Event Horizon Telescope, a planet-spanning array of radio dishes, captured the first image of a black hole's shadow in 2019. The target was M87 star, a supermassive black hole 55 million light-years distant, containing 6.5 billion solar masses. Its Schwarzschild radius spans roughly 19 billion kilometers, larger than the orbit of Pluto. The image revealed a bright ring of superheated gas surrounding a dark central region, the shadow cast by the event horizon against the glowing accretion disk. This shadow measured approximately 42 microseconds across, an angular size equivalent to viewing a donut on the moon from Earth. The asymmetry in the ring's brightness arises from relativistic beaming. Gas orbiting the black hole at velocities approaching the speed of light appears brighter when moving toward the observer and dimmer when moving away. The bottom of M87's ring glows brighter because material there moves toward Earth, its light blue-shifted and intensified. The top appears dimmer, its light red-shifted and weakened. This asymmetry confirms that matter orbits the black hole at the extreme velocities general relativity predicts. Time near M87 star dilates to extraordinary degrees. At the innermost stable circular orbit, located at 3 Schwarzschild radii for a non-rotating black hole, time passes at roughly 82% the rate of distant observers. But M87 star rotates, dragging spacetime with it in a phenomenon called frame dragging. This rotation allows stable orbits closer to the horizon, where time dilation becomes more severe. Gas spiraling inward experiences progressively slower time, its atoms vibrating at frequencies that appear red-shifted to distant telescopes. The universe contains an estimated 100 million stellar mass black holes in the Milky Way alone, remnants of massive stars that exhausted their fuel over the galaxy's 13 billion-year history. Supermassive black holes anchor the centers of most large galaxies, their masses ranging from millions to tens of billions of solar masses. Each represents a region where time, as measured by distant observers, slows toward stillness, where the future bends inward, where the architecture of space-time reveals its most extreme possibilities. The boundary that separates these regions of extreme temporal distortion from the rest of the universe carries a name that describes its fundamental property with mathematical precision. The event horizon marks not a physical surface, but a causal boundary, a sphere in space-time beyond which events can never influence the outside universe. Light emitted from within this boundary, traveling at 299,792 kilometers per second, nonetheless fails to escape, not because it slows down, but because space-time itself curves so severely that all paths lead inward. The geometry of this boundary emerges directly from the equations Carl Schwarzschild solved in 1916, just months after Einstein published his field equations of general relativity. Schwarzschild, serving as an artillery officer on the Russian front during World War I, found an exact solution describing the space-time around a spherically symmetric, non-rotating mass. The mathematics revealed a critical radius at which the escape velocity equals the speed of light. For any object compressed within this radius, the event horizon forms automatically, a consequence of geometry rather than material properties. the Schwarzschild radius scales linearly with mass. For the Sun, this critical radius measures approximately 2.95 kilometers. For Earth, it shrinks to merely 8.87 millimeters, roughly the size of a marble. The supermassive black hole at the center of the Milky Way, Sagittarius, a star with its 4 million solar masses, possesses an event horizon spanning approximately 12 million kilometers, comparable to the orbit of Mercury around the Sun. The black hole M87 star, imaged by the Event Horizon Telescope in 2019, contains 6.5 billion solar masses, stretching its horizon to 19 billion kilometers, larger than the orbit of Pluto. The nature of this boundary defies everyday intuition about surfaces and edges. An astronaut crossing the event horizon of a sufficiently large black hole would notice nothing remarkable at the moment of crossing. No membrane, no barrier, no sudden change in local physics. The curvature of space-time at the horizon of a supermassive black hole remains gentle enough that tidal forces pose no immediate threat. For M87 star, the tidal acceleration at the horizon measures less than 1/10,000th of Earth's surface gravity, barely perceptible to human senses. Yet this crossing represents an irreversible transition, a one-way passage through a causal boundary. The mathematics reveals why, through the behavior of light cones, those geometric structures that define which events can influence which other events. Outside the horizon, light cones tilt slightly toward the black hole, but still permit escape trajectories. At the horizon itself, the outward pointing edge of the light cone becomes vertical in spacetime diagrams, meaning that light traveling directly away from the black hole makes no progress outward. Inside the horizon, all light cones tilt so severely that every possible future trajectory leads towards the central singularity. This tilting of light cones transforms the nature of space and time within the horizon. The radial coordinate, which outside the horizon represents a spatial direction, acquires the mathematical properties of time inside. The singularity at the center becomes not a place in space, but a moment in time, an unavoidable future that all infalling matter must eventually reach. Just as observers outside a black hole cannot avoid moving forward in time, observers inside cannot avoid moving toward smaller radial coordinates, toward the singularity. The time required to reach this inevitable destination depends on the black hole's mass. For a stellar mass black hole of 10 solar masses, the journey from horizon to singularity lasts approximately 0.0001 seconds, as measured by the infalling observer's clock. For Sagittarius A star, this duration extends to roughly 20 seconds. For the largest known black holes, exceeding 60 billion solar masses, the infalling observer might survive for several hours before reaching the central singularity, though the physics of that final approach remains beyond current theoretical understanding. From the perspective of a distant observer, the crossing of the event horizon appears profoundly different. Light emitted by an infalling object experiences progressively greater gravitational redshift as the object approaches the horizon. Photons emitted at 90% of the Schwarzschild radius arrive at distant telescopes with wavelengths stretched by a factor of approximately 3.2. At 99% of the horizon radius, this factor grows to roughly 10. At 99.9%, It exceeds 31. This redshift carries energy away from the photons. Light that began as visible radiation shifts into infrared, then into radio waves, its frequency dropping, its energy diminishing. Simultaneously, the rate at which photons escape decreases as time dilation intensifies. The combined effect causes the infalling object to fade from view asymptotically, growing dimmer and redder, but never quite disappearing. The final photons emitted just before horizon crossing take progressively longer to climb out of the gravitational well, their arrival times stretching toward infinity. This asymptotic fading explains why distant observers never witness the actual formation of an event horizon in finite time. A collapsing star, compressing under its own gravity after exhausting nuclear fuel, appears to freeze just above the Schwarzschild radius, its surface redshifting into invisibility. The horizon forms in the infinite future of external time, yet the star has already crossed it in its own proper time. This apparent paradox dissolves when space-time is understood as a unified geometric structure rather than separate containers of space and time. The causal isolation imposed by the event horizon creates what physicists call an information paradox, a tension between general relativity and quantum mechanics that remains unresolved. Quantum mechanics requires that information about physical systems be preserved, encoded in the quantum states of particles. Yet matter crossing the event horizon carries information into a region causally disconnected from the outside universe. When Stephen Hawking demonstrated in 1974 that black holes emit thermal radiation through quantum effects near the horizon, the paradox sharpened. This Hawking radiation carries no information about what fell in, suggesting that information might be destroyed, violating a fundamental principle of quantum theory. The temperature of this radiation depends inversely on the black hole's mass. A stellar mass black hole of 10 solar masses radiates at approximately 6 times 10 to the -9th Kelvin, far colder than the 2.7 Kelvin cosmic microwave background that bathes it. Such a black hole absorbs more energy from its surroundings than it emits, growing rather than shrinking. Only black holes less massive than the Moon would radiate faster than they absorb in the current universe, their temperatures exceeding the cosmic background. The event horizon thus represents more than a boundary in space. It marks a frontier of causality, a surface where the future becomes geometrically constrained, where time itself bends toward an inescapable conclusion. The mathematics that describes this boundary connects to the deepest questions about the nature of information, the relationship between gravity and quantum mechanics, and the ultimate fate of matter that ventures too close to these cosmic drains in the fabric of space-time. The fabric of space-time does not merely curve and warp in response to mass. It vibrates, it ripples, it carries disturbances across the cosmos at precisely the speed of light, transmitting information about the most violent events in the universe through oscillations so subtle that detecting them required the most sensitive instruments humanity has ever constructed. Einstein himself predicted these waves in 1916, just months after completing his general theory of relativity. The mathematics emerged naturally from his field equations, showing that accelerating masses must produce propagating disturbances in the geometry of space-time itself. Yet Einstein doubted whether these ripples would ever be detected. He calculated that even the most energetic astronomical events would produce waves so faint by the time they reached Earth that no conceivable technology could measure them. The amplitude of a gravitational wave from a distant cosmic collision might stretch and compress space by less than the width of a proton across the entire diameter of our planet. The mechanism that generates these waves follows from the same principles that govern electromagnetic radiation. Just as an accelerating electric charge produces electromagnetic waves, an accelerating mass produces gravitational waves. But the comparison reveals an important asymmetry. Electromagnetic waves arise from the oscillation of dipoles, from the separation of positive and negative charges. Gravitational waves require quadrupole oscillations, the stretching and squeezing of mass distributions, because gravity knows only one sign. There is no negative mass to create a gravitational dipole. This mathematical constraint means that gravitational radiation emerges only from the second derivative of the mass distribution, making it inherently weaker than its electromagnetic counterpart. The weakness of gravitational waves reflects the weakness of gravity itself. The gravitational force between two protons is approximately 10 to the 36th power times weaker than the electromagnetic force between them. This disparity propagates into the radiation these forces produce. A gravitational wave carrying the same energy as a radio transmission would require a source billions of times more massive, accelerating at relativistic speeds. Nature provides such sources in the form of compact binary systems, pairs of neutron stars or black holes locked in orbital decay. The Hulse-Taylor binary, discovered in 1974, consists of two neutron stars orbiting each other with a period of 7 hours and 45 minutes. Each neutron star packs roughly 1.4 solar masses into a sphere only 20 kilometers across, creating gravitational fields intense enough to produce measurable effects. The orbital period of this system decreases by approximately 76 microseconds per year, matching Einstein's prediction for energy loss through gravitational radiation to within 1/3 of 1%. The system radiates roughly 7 times 10 to the 24th watts in gravitational waves, energy drawn from the orbital motion itself, causing the two stars to spiral gradually inward. The direct detection of gravitational waves required a different approach than observing their indirect effects on orbital dynamics. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, achieved this milestone on September 14, 2015, recording a signal that had traveled 1.3 billion light-years across the cosmos. The source was a binary black hole merger, two black holes of approximately 36 and 29 solar masses, spiraling together and coalescing into a single black hole of 62 solar masses. The missing 3 solar masses, equivalent to the energy content of 5 times 10 to the 47 joules, had been radiated away as gravitational waves in a fraction of a second. The signal lasted 0.2 of a second, sweeping upward in frequency from 35 Hz to 250 Hz as the black holes completed their final orbits. During the last milliseconds before merger, the two objects were circling each other at nearly half the speed of light, completing dozens of orbits per second. The gravitational wave amplitude peaked at a strain of approximately 1 part in 10 to the 21st, meaning that the 4-kilometer arms of the LIGO detectors stretched and compressed by less than 1/10,000th the diameter of a proton. Detecting such infinitesimal changes required isolating the mirrors at the ends of the interferometer arms from every conceivable source of noise. Seismic vibrations, thermal fluctuations in the mirror coatings, quantum uncertainty in the laser light itself, all threatened to overwhelm the gravitational wave signal. The mirrors hang from quadruple pendulum systems that filter out ground motion by factors exceeding 10 billion at the frequencies of interest. The laser beams bounce between the mirrors approximately 300 times, effectively extending the arm length to 1,200 kilometers and amplifying the phase shift produced by a passing wave. The geometry of gravitational waves differs fundamentally from electromagnetic waves. Light oscillates transversely, with electric and magnetic fields perpendicular to the direction of propagation. Gravitational waves also oscillate transversely, but they stretch space in one direction while compressing it in the perpendicular direction, then reverse this pattern half a cycle later. This quadrupole pattern means that a circular ring of test particles would be deformed into an ellipse, then back to a circle, then into an ellipse oriented at 90 degrees to the first, as a gravitational wave passes through. The two polarization states of gravitational waves, designated plus and cross, rotate this stretching pattern by 45 degrees relative to each other. LIGO's L-shaped configuration is optimally sensitive to one polarization when the wave arrives from directly overhead. But the network of detectors spanning the globe allows astronomers to determine both the polarization and the source direction of incoming signals. The addition of the Virgo detector in Italy and Kagra in Japan has transformed gravitational wave astronomy from detection to precision measurement. The merger of neutron stars produces gravitational waves accompanied by electromagnetic counterparts, light across the spectrum from gamma rays to radio waves. On August 17, 2017, LIGO and Virgo detected a gravitational wave signal designated GW170817, originating from a neutron star collision 130 million light-years away in the galaxy, NGC 4993. Within 2 seconds, the Fermi satellite detected a short gamma ray burst from the same location. Over the following days and weeks, telescopes across the world observed the kilonova, the radioactive glow of heavy elements forged in the collision. This single event confirmed that neutron star mergers produce the heaviest elements in the periodic table, including gold, platinum, and uranium, through rapid neutron capture processes that cannot occur in ordinary stellar environments. The gravitational waves from this merger arrived 1.7 seconds before the gamma rays, after traveling for 130 million years. This tiny delay, consistent with both signals traveling at the speed of light through intergalactic space, constrained the difference between the speed of gravity and the speed of light to less than 1 part in 10 to the 15th power. Einstein's prediction that gravitational waves propagate at exactly the speed of light, made a century earlier, had been verified to extraordinary precision. The universe hums with gravitational waves at frequencies far below what LIGO can detect. Supermassive black hole binaries containing millions to billions of solar masses, produce waves with periods measured in years to decades. Detecting these requires a different kind of instrument, one that uses the universe itself as a detector. Pulsar timing arrays monitor the arrival times of radio pulses from dozens of millisecond pulsars scattered across the galaxy. A passing gravitational wave would stretch and compress the space between Earth and these pulsars, causing systematic variations in pulse arrival times correlated across the array. In 2023, pulsar timing collaborations announced evidence for a gravitational wave background, a cosmic hum produced by the superposition of waves from countless supermassive black hole binaries throughout the universe. The characteristic strain of this background, approximately 10 to the negative 15 at frequencies of 1 cycle per year, represents the integrated gravitational wave emission from binary systems that formed when galaxies merged over cosmic history. The fabric of spacetime thus carries within it the record of the universe's most energetic events. Every black hole merger, every neutron star collision, every supernova asymmetry sends ripples propagating outward at the speed of light, stretching and compressing space by amounts almost too small to imagine. These waves pass through matter without significant absorption, traveling billions of light years with their information intact, whispering the secrets of cosmic violence to instruments sensitive enough to listen. Yet while these gravitational waves propagate through the cosmos carrying information about distant cataclysms, they travel in a direction that reveals something profound about the nature of reality itself. The waves move outward from their sources, never inward. The ripples expand, never contract. This asymmetry, so obvious that it might seem unremarkable, points toward one of the deepest mysteries in physics: the arrow of time. The fundamental equations that govern the behavior of matter and energy possess a curious property. They work equally well whether time runs forward or backward. Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's field equations of general relativity, even the Schrödinger equation of quantum mechanics, all remain mathematically valid if the direction of time reverses. A film of 2 billiard balls colliding, played in reverse, shows physics that violates no fundamental law. The equations cannot distinguish between past and future, yet experience reveals an unmistakable directionality. Eggs break, but do not spontaneously reassemble. Coffee cools, but does not spontaneously heat. Stars radiate light outward into space, never absorbing coherent radiation from all directions to grow brighter. The universe exhibits a clear distinction between what came before and what comes after, a distinction that the fundamental equations seem unable to explain. The resolution to this apparent paradox emerged from the work of Ludwig Boltzmann in the late 19th century, building on earlier insights by Rudolf Clausius and others. The key lies not in the laws governing individual particles, but in the statistical behavior of vast collections of particles. The arrow of time emerges from probability, from the overwhelming likelihood that systems evolve from less probable states to more probable ones. Consider a box divided by a partition, with all the gas molecules initially confined to one half. When the partition is removed, the molecules spread throughout the entire volume. They do not spontaneously return to 1/2 because such a configuration is extraordinarily improbable. For a box containing Avogadro's number of molecules, approximately 6 times 10 to the 23rd particles, the probability of all molecules randomly occupying only half the volume equals roughly 1 in 10 to the 23rd power 1 divided by 2 raised to the power of 6 times 10 to the 23rd. This number is so vanishingly small that writing it would require more zeros than there are particles in the observable universe. This statistical tendency toward more probable configurations defines the quantity that Clausius named entropy. In precise terms, entropy measures the logarithm of the number of microscopic arrangements that correspond to a given macroscopic state. A gas spread uniformly through a container has high entropy because countless different arrangements of individual molecules produce the same uniform appearance. A gas confined to half the container has lower entropy because fewer microscopic configurations achieve this ordered state. The second law of thermodynamics, perhaps the most universal principle in all of physics, states that the total entropy of an isolated system never decreases. It may remain constant in idealized reversible processes, but in all real processes, entropy increases. This law emerges not from the fundamental equations of motion, but from the statistics of large numbers. It represents not an absolute prohibition, but an overwhelming probability. So overwhelming that violations, while technically possible, would require waiting times exceeding the age of the universe by factors beyond comprehension. The numerical precision of this law manifests throughout physical systems. When heat flows from a hot object at temperature T, hot to a cold object at temperature T cold, the entropy increase equals the heat transferred divided by T cold minus the same heat divided by T hot. For a cup of coffee at 350 Kelvin cooling to room temperature, at 295 Kelvin by transferring 50,000 joules of thermal energy, the entropy of the universe increases by approximately 26 joules per Kelvin. This increase is irreversible in any practical sense. The connection between entropy and information, formalized by Claude Shannon in 1948 and deepened by subsequent researchers, reveals that entropy measures missing information about a system's microscopic state. A low entropy configuration carries more information because knowing the macroscopic state constrains the possible microscopic arrangements more tightly. The spreading of gas, the cooling of coffee, the breaking of eggs, all represent the loss of information about precise particle positions and velocities, the erasure of correlations that once existed. This information-theoretic perspective illuminates why memory and records point only toward the past. A photograph records the configuration of objects at an earlier time because the photographic process increased entropy. Light scattered from objects, chemical reactions occurred in the film, heat dissipated into the environment. The creation of any record requires entropy increase, which means records can only form in the direction of increasing entropy. Memory itself, encoded in neural connections and synaptic strengths, exists because biological processes dissipate energy and increase entropy. The arrow of time thus emerges from thermodynamics, but this raises a deeper question. Why did the universe begin in a low entropy state? The second law explains why entropy increases, but not why it started low enough to permit billions of years of increase. The early universe, despite its apparent uniformity and high temperature, possessed remarkably low gravitational entropy. Matter spread smoothly through space represents a highly improbable configuration when gravity is considered, because gravity tends to clump matter together. The entropy of the observable universe today measures approximately 10 to the 103rd power in natural units, a number dominated by the entropy of supermassive black holes. The black hole at the center of the Milky Way alone contributes roughly 10 to the 90th power units of entropy. Yet this enormous value remains far below the maximum possible entropy, which would be achieved if all matter collapsed into a single black hole. The universe began with gravitational entropy near zero and has been increasing ever since, with structure formation, the clumping of matter into stars, galaxies, and black holes, representing the primary mechanism of entropy production. This cosmological arrow of time aligns with the thermodynamic arrow, the electromagnetic arrow that causes radiation to propagate outward from sources, and the psychological arrow that gives humans the sensation of time flowing from past to future. Whether these arrows are fundamentally connected or merely correlated remains an open question, though most physicists suspect a deep relationship rooted in the boundary conditions of the universe. The rate of entropy increase varies dramatically across different processes. A supernova explosion increases entropy by roughly 10 to the 52nd power joules per Kelvin in a matter of seconds. The formation of a stellar mass black hole from gravitational collapse increases entropy by approximately 10 to the 77th power in natural units. The eventual evaporation of that black hole through Hawking radiation, occurring over timescales of 10 to the 67th years, will further increase entropy as the organized gravitational configuration disperses into thermal radiation. On human scales, the entropy production of a living organism illustrates the local decrease in entropy that life achieves at the cost of greater entropy increase in the environment. A human body maintains its ordered structure by consuming approximately 2,000 kilocalories per day, converting chemical energy into heat that dissipates into the surroundings. The entropy decrease within the body, perhaps 100 joules per Kelvin daily, is vastly exceeded by the entropy increase in the environment, roughly 25,000 joules per Kelvin from metabolic heat alone. Life does not violate the second law. It exploits the entropy gradient between low-entropy sunlight and high-entropy thermal radiation to maintain temporary islands of order. The flow of time, so fundamental to experience, thus emerges from the statistical behavior of matter and energy in a universe that began in an extraordinarily improbable state. Each moment carries the universe further from that initial condition, closer to the equilibrium of maximum entropy, where no gradients remain to drive change, where the distinction between past and future finally dissolves into timeless uniformity. That dissolution into equilibrium lies inconceivably far in the future, separated from the present moment by spans of time that dwarf all human comprehension. But the question of how much time has already passed, how long the universe has existed since that initial state of extraordinary low entropy, yields to careful measurement and reveals a number both humbling and precise. The universe is 13.787 billion years old, with an uncertainty of only 20 million years in either direction. This figure, refined through decades of observation and calculation, represents one of the most remarkable achievements of modern cosmology. To measure the age of something that predates not only human civilization but the Earth itself, the solar system, and even the oldest stars visible in the night sky, requires methods that transform light into a cosmic clock. The first approach to cosmic chronology emerged from the observation that the universe is expanding. In 1929, Edwin Hubble documented what earlier astronomers had suspected. Distant galaxies are receding from the Milky Way, and the more distant they are, the faster they recede. This relationship, now called Hubble's law, states that a galaxy's recession velocity equals its distance multiplied by a constant. That constant, the Hubble parameter, currently measures approximately 70 kilometers per second per megaparsec. A galaxy 100 megaparsecs away, roughly 326 million light-years distant, recedes at about 7,000 kilometers per second. Running this expansion backward in time leads to an inescapable conclusion. If galaxies are flying apart today, they must have been closer together yesterday, and closer still the day before. Extrapolating this contraction to its logical endpoint suggests a moment when all the matter and energy in the observable universe occupied the same location. The inverse of the Hubble parameter provides a rough estimate of when this occurred. Dividing 1 by 70 kilometers per second per megaparsec yields approximately 14 billion years. This naive calculation, called the Hubble time, offers a first approximation to the age of the cosmos, but the expansion has not proceeded at a constant rate. For most of cosmic history, the mutual gravitational attraction of matter slowed the expansion, like a ball thrown upward, gradually decelerating as Earth's gravity pulls it back. This deceleration means the universe expanded faster in the past than it does today, which implies the actual age is somewhat less than the Hubble time. Accounting for this gravitational braking reduces the estimated age by roughly 1 billion years. Then, approximately 5 billion years ago, something changed. The expansion stopped decelerating and began accelerating. Some component of the universe, now called dark energy, exerts a repulsive gravitational effect that overwhelms the attractive gravity of matter on cosmic scales. Dark energy constitutes approximately 68% of the total energy content of the universe, with dark matter contributing 27% and ordinary atomic matter only 5%. Incorporating dark energy's accelerating influence into the age calculation adjusts the figure to the currently accepted value of 13.787 billion years. Independent confirmation of this age comes from the oldest objects astronomers can study directly. Globular clusters, dense spherical collections of hundreds of thousands of stars orbiting the Milky Way, contain some of the most ancient stellar populations in the universe. The stars in these clusters formed from primordial gas clouds shortly after the first generation of stars enriched the cosmos with heavy elements. By measuring the luminosity and color of stars in globular clusters and comparing these observations to theoretical models of stellar evolution, astronomers can estimate when these stars ignited their nuclear furnaces. The oldest globular clusters in the Milky Way contain stars approximately 12.5 to 13 billion years old. This figure provides a lower limit on the age of the universe. The cosmos must be at least as old as its oldest stars. The consistency between this stellar age and the cosmological age derived from expansion measurements offers powerful confirmation that both methods are capturing the same underlying reality. The most precise measurement of cosmic age comes from the cosmic microwave background radiation, the afterglow of the hot, dense state that existed 380,000 years after the Big Bang. At that epoch, the universe had cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms. Before this recombination, photons scattered constantly off free electrons, unable to travel far before encountering another charged particle. After recombination, the universe became transparent, and light could travel freely across space. That ancient light, stretched by the expansion of the universe from visible wavelengths to microwaves, now bathes the cosmos uniformly from all directions. Its temperature measures 2.725 Kelvin, just 2.725 degrees above absolute zero. But this temperature is not perfectly uniform. Tiny fluctuations, variations of only 1 part in 100,000, encode information about the physical conditions of the early universe. The Planck satellite, launched by the European Space Agency in 2009, mapped these temperature fluctuations with unprecedented precision. The pattern of hot and cold spots across the sky reflects acoustic oscillations in the primordial plasma, sound waves that traveled through the early universe before recombination froze them in place. The angular size of these fluctuations depends on the geometry of the universe, the density of matter and energy, and the rate of expansion. By fitting theoretical models to the observed pattern, cosmologists extract the parameters that govern cosmic evolution, including the age of the universe. The Planck measurements yield an age of 13.787 billion years, with a precision of 0.15%. This uncertainty of only 20 million years represents a remarkable achievement, determining when the universe began to within a fraction of a percent, using light that has traveled for nearly the entire history of the cosmos. Converting this vast span into more familiar units reveals its immensity. The universe has existed for approximately 4.35 times 10 to the 17th seconds. If each second were compressed into a single year, the age of the universe would still exceed 13 trillion years. The oldest rocks on Earth, zircon crystals from Western Australia, date to 4.4 billion years, making them only 32% as old as the cosmos itself. The dinosaurs went extinct 66 million years ago, a mere 0.5% of cosmic history. All of recorded human civilization, roughly 5,000 years, represents 0.000036% of the time since the Big Bang. The light arriving from the most distant observable objects has traveled for nearly this entire duration. The galaxy GN-Z11, discovered by the Hubble Space Telescope in 2016, emitted its light 13.4 billion years ago, when the universe was only 400 million years old. Looking at GNZ11 is looking back through 97% of cosmic history, observing a galaxy as it appeared when the universe was only 3% of its current age. This relationship between distance and time creates the observable universe, a sphere centered on Earth with a radius determined by how far light has traveled since the Big Bang. But the expansion of space complicates this calculation. Light that has traveled for 13.4 billion years has not crossed 13.4 billion light-years of space. The space itself has expanded during the journey, stretching the distance between the photon's origin and its destination. GNZ11 now lies approximately 32 billion light-years away, carried to that distance by the expansion that occurred while its light traveled toward Earth. The edge of the observable universe, the cosmic microwave background, lies even farther. The light from that surface has traveled for 13.8 billion years, but the matter that emitted it now resides 46.5 billion light-years away. The observable universe thus spans 93 billion light-years in diameter, a sphere containing approximately 2 trillion galaxies, each with hundreds of billions of stars. That sphere of observable reality, vast beyond comprehension yet finite in its extent, represents only the portion of the cosmos from which light has had time to reach Earth since the universe began. Beyond that boundary lies more space, more galaxies, more time unfolding in regions forever hidden from observation. And the fate of all this time, the ultimate destiny of the temporal dimension itself, depends entirely on how the expansion of space proceeds across the billions and trillions of years that stretch ahead. The expansion that Edwin Hubble first measured in 1929 continues today, carrying galaxies apart at velocities proportional to their distances. A galaxy 1 megaparsec away recedes at approximately 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. This relationship, encoded in the Hubble constant, means that sufficiently distant objects recede faster than light itself can travel through space. Not because they move through space at superluminal velocities, but because the space between them and Earth grows faster than photons can cross it. This expansion rate determines how time will unfold across cosmic history. For decades, astronomers assumed the expansion must be slowing. The mutual gravitational attraction of all matter in the universe acting as a cosmic brake, gradually reducing the recession velocities of distant galaxies. The question seemed simple. Did the universe contain enough matter to halt the expansion entirely, causing an eventual collapse? Or would expansion continue forever, gradually slowing but never stopping? The answer, discovered in 1998 through observations of Type Ia supernovae by 2 independent research teams, overturned all expectations. The expansion is not slowing, it is accelerating. Distant supernovae appeared fainter than their redshifts predicted, indicating they had traveled farther than expected, pushed to greater distances by an expansion that had sped up over cosmic time. Something was driving the universe apart with increasing vigor, something that came to be called dark energy. This dark energy, whatever its fundamental nature, constitutes approximately 68% of the total energy content of the universe. It permeates all of space, exerting a negative pressure that causes expansion to accelerate rather than decelerate. Its density remains constant as space expands, meaning that as the universe grows larger, the total amount of dark energy increases proportionally. Matter dilutes as space stretches, becoming less influential over time, while dark energy maintains its strength, gradually dominating the cosmic evolution. The consequences for the fate of time unfold across timescales that reduce human history to an imperceptible flicker. In approximately 100 billion years, the accelerating expansion will carry all galaxies beyond the local group past the cosmic horizon. The light they emit will never reach the Milky Way, red-shifted into oblivion by the stretching of space. Observers in that distant epoch will see only the merged remnant of the local group, a single giant elliptical galaxy surrounded by an apparently empty universe. The cosmic microwave background, that ancient echo of the universe's first light, will redshift beyond detection. The evidence that once revealed the Big Bang will fade into unobservable wavelengths, leaving future astronomers with no indication that the universe ever had a beginning. The night sky will darken as distant galaxies vanish beyond the horizon, their light stretched to wavelengths longer than the observable universe itself. Within the surviving galaxy, stellar evolution will continue for trillions of years. Red dwarf stars, those dim embers that burn their hydrogen fuel with miserly efficiency, will shine for 10 trillion years or more. Proxima Centauri, currently 4.24 light-years from Earth, will continue fusing hydrogen long after the Sun has cooled to a white dwarf, long after that white dwarf has faded to a black dwarf, long after the Milky Way and Andromeda have merged into a single stellar system. But even red dwarfs eventually exhaust their fuel. By 100 trillion years after the Big Bang, the last stars will flicker out, leaving behind a universe populated only by stellar remnants. White dwarfs will cool toward absolute zero, their temperatures dropping by fractions of degrees across billions of years. Neutron stars will spin down, their magnetic fields weakening, their rotation rates declining until they become cold, dark spheres of degenerate matter. Black holes will persist, growing slowly through the occasional capture of wandering remnants. Time in this dark era will pass with excruciating slowness from any perspective tied to physical processes. The fastest events will be the rare gravitational captures, the occasional merger of stellar remnants, the slow evaporation of black holes through Hawking radiation. A stellar mass black hole, one containing perhaps 10 solar masses, will require approximately 10 to the 67th power years to evaporate completely, releasing its mass energy as a faint glow of thermal radiation at temperatures measured in billionths of a degree above absolute zero. Supermassive black holes, those monsters containing millions or billions of solar masses, will endure far longer. The black hole at the center of the merged Milky Way Andromeda system, grown to perhaps 100 billion solar masses through billions of years of galactic mergers, will require approximately 10 to the 100th power years to evaporate. That number, a Google years, exceeds the current age of the universe by a factor of 10 to the power of 90. Time will continue to pass, moment following moment, but the events that mark its passage will become vanishingly rare. The final fate of matter itself remains uncertain, dependent on physics not yet fully understood. Protons, the building blocks of atomic nuclei, may be unstable on timescales of 10 to the 34th to 10 to the 40th years. If proton decay occurs, all ordinary matter will eventually dissolve into radiation and lighter particles, leaving nothing but black holes, electrons, positrons, and photons drifting through an ever-expanding void. Even after the last black holes evaporate, time will continue. The universe will approach but never quite reach thermal equilibrium, a state of maximum entropy where no gradients exist to drive physical processes. Photons will redshift towards zero energy, their wavelengths stretched across distances larger than the observable universe. The temperature will asymptotically approach absolute zero, declining by imperceptible fractions across timescales that make the current age of the universe seem instantaneous. This ultimate fate, sometimes called the heat death, represents not an end to time, but a transformation of its character. Time will continue to pass, second following second, year following year, but nothing will happen to distinguish one moment from another. The arrow of time, that asymmetry between past and future driven by increasing entropy, will fade as entropy approaches its maximum value. The distinction between earlier and later will become physically meaningless, not because time stops, but because the universe will have exhausted all possibilities for change. Yet this projection assumes the current understanding of dark energy remains valid across all future epochs. If dark energy strengthens over time, a scenario called phantom energy, the acceleration could increase without bound, eventually tearing apart galaxies, then solar systems, then planets, then atoms themselves in a final catastrophic expansion called the Big Rip. Current observations slightly favor a cosmological constant, dark energy with constant density, but the uncertainty leaves room for more dramatic endings. The mathematics of general relativity permits other possibilities as well. The universe might undergo a phase transition, a sudden change in the properties of the vacuum that would propagate outward at the speed of light, transforming the laws of physics themselves. Such an event could occur at any moment without warning, rewriting the rules that govern matter and energy throughout the cosmos. For now, time continues its steady passage, each moment flowing into the next with the same reliability that has characterized the universe since its first instance. The clocks that measure this passage, whether atomic oscillations or pulsar rotations or the slow cooling of white dwarfs, will eventually fall silent. But the dimension they measure, that fourth coordinate of spacetime that Einstein wove together with the three dimensions of space, will persist as long as the universe itself endures. The fabric of reality, curved by mass and stretched by expansion, carries within it the record of all that has occurred and the potential for all that might yet happen. From the Planck time of 5.39 times 10 to the negative 44th seconds to the Google years of black hole evaporation, time spans a range of scales that defies intuition. And through it all, the same equations govern its behavior. The same geometry describes its structure. The same physics determines its fate.